Alright, so a little late, but I did get a working solution for yesterday's deal. So I thought I had something that was a little faster than this, like um, this ended up being n squared, I want to say, but I thought I could have something that was n. How fast was the other one that I was thinking of? It was almost linear, I think, but I don't think, well, it didn't work out. So what I ended up doing was um, basically this one uses a monotonic stack, a different monotonic stack for every subsequent point in the list. So monotonic stack, if you do a one pass, it'll be linear. It'll be like O of n. But obviously, if you're but if you have a different stack for every point as the endpoint, so like a monotonic stack that passes through the first points, the first 2 points, the first 3 points, the first 4 points, different stack for each, basically, then it's going to be n squared. So how this one works is if I were to start by sorting the points in increasing x coordinates. So at that point, for any given point on the list, you're going to go, it's going to form as possibly the bottom left, or sorry, the bottom right corner. And it's going to form the bottom right corner by looking at the previous points as being the top left corner possibly, as long as it doesn't get kind of hidden by another triangle or another rectangle. So for instance, if you have these 3 points and you're going by A, B, C, A obviously can't do another point with itself, so B can form a rectangle with A, and then C is going to check to see if it can form a rectangle with B. It does. And then it's going to check to see if it forms a rectangle with A, and it needs to somehow determine that point B blocks it. But if point A was like a little lower, like maybe 0, I guess instead of 2, 6, maybe 2, 3, then the point here 2, 6, 2 would climb up, but not kind of be hidden by the rectangle of 4, 4. So I thought I could find something better than that, but not being that. So so here are the key points here. I find the number of points where, in order to have any sort of possible rectangle be formed from a given bottom right corner to some previous top left corner, that top left corner has to be a bigger y value. So this is a slight optimization. I'm going to find the first point in the sorted list that is track first prior index in sorted list where y coordinate is higher, which is i.e. first earlier possible rectangle. Previous bigger is the first index prior to this index where the y value is bigger. And here note that I sort by increasing x's but also decreasing y's. So if you have the same x coordinate but multiple y, well, same x coordinate but different y coordinates, right? So let's say it's like 2, 1, 2, 2, 2, 3. Then it'll be in the sorted list 2, 3, 2, 1, 2, or 2, 3, 2, 2, 2, 1. So it's going to descendingly have the y's, which makes sense in this if you're trying to kind of logically think about y values needing to increase in order to form that rectangular, or I guess in this case, upper left line, vertical line. So anyways, this is previous bigger, and to get the previous bigger from any index, I'm going to create a, this is going to be a decreasing monotonic stack of tuples, where the tuples is the y coordinate and the index of that. I don't need to track the x coordinate because I'm already iterating through the points in order, in sorted order of the x. So the x coordinates are already kind of implied to be sorted, to be kind of increasing. So for every index in the range n, I get the point at the index, and then this thing has a kind of place, I call it dummy big value to block block stack from fully emptying. So in examples of monotonic stacks that I've seen, they generally have a check for if the stack is empty in order for it to do any comparisons of the current value to the previous stack value in order to pop the top of the stack. But this dummy value just prevents the stack from fully emptying, so you never have to check for an empty stack. It basically will always fail to pop this value off the top. In case this is going to be infinity and -1 is the index. So -1 being the index because once it fails to pop the top of the stack, that should indicate the index where you find the previous higher y value. And in this case, you never find a previous higher y value, so the index would be -1. If it was 0, then technically you'd be saying that you can find a higher y coordinate than this the y coordinate at this point at index 0. So with monotonic stacks, you have a while loop that will pop the top of the stack if it would break the kind of property that the stack is trying to maintain. In this case, the stack is trying to maintain property where values in the stacks are decreasing. So that means that if the current y value would actually be increasing, so the current y value is bigger than the top of the stack, then pop the top of the stack. So like if top of the stack is 5 and the current value is 10, you can't put 10 on top of 5 on the stack. That'd make 5 10. That'd be an increasing stack. So you'd pop the 5, and in theory there might be something bigger than the 5 on the stack. Let's say the stack is 25 and the current y value is 10, so you pop the 5 off. Then you compare 20 to 10, and you say 20 is smaller than 10, so that's fine. Or 20 is not smaller than 10, so that would stop the while loop, and then you push 10 onto the stack, so it'd be 2010 after that. So anyways, it pops off any smaller values than the current y that would prevent it from being decreasing, and then the stack should have the information for where there's a previous index of higher y value. So previous bigger at the index at this index where this point is found, I'm going to keep store into it the index where the previous y value is found, the previous bigger y value is found, and then push onto the stack the current tuple, that is the current y value and the current index. So that's the decreasing monotonic stack. And then for usage of that to actually solve this issue, what we would do is we're going to iterate through the points in sorted order from left to right. Get the point at the current index. Jump to the index of the previously bigger y value. So the first y value that's bigger from this point to the left. That'll be kind of the first instance where I can form that rectangle. If there is none, so if the previous index where you can find a y value is actually not there, -1 is the index, then just skip this point. There's no way that this thing, so if it's like a increasingly ordered kind of point-wise to the top right, then for each of these points there is no previously bigger one. So it can't form any triangles or rectangles. But if there was one, so the index is not -1, so it doesn't just go to the next loop, the answer is going to be automatically incremented 1. There's going to be one answer at least. I'm going to set that y value of that previous point to be the current y. So, for instance, it's going to, if I'm at point C and it sees this previously bigger one at point B, then whatever the y value is at, let's say 4 is going to be the current y. And if you think about later ways of actually forming rectangles, the rectangle has to form with a height that is between the height of this point and the height of this point. So between the height of B and the height of C here. So the height of C is y, current y coordinate, and then the height of B is current y. So iterating through every single possible index prior to this, prior to the previous index, all the way down to -1. So while not -1, if the y coordinate of this previous index is between the y's of the current point and or y of this of the point I'm inspecting versus the current y, which is the current triangle point or current rectangle point, then reset the current y to be whatever the y coordinate is of this current point, and then the answer is incremented by 1 because this now constitutes a new rectangle. And then obviously go ahead and decrement the previous. I guess maybe I could use a for loop here because I do need to iterate through everything. Sure. Let me go and change that. For some reason, it made more sense in my head to start with I think it's probably because I use previous as the index, and previous is initially I'll say P in, gosh, let's say start is this thing. Okay, in range of start, -1, -1. So if the y of say previous, actually, I think that's right. Okay. Okay. So if the y actually this doesn't really maintain a different monotonic stack. I was thinking this is actually monotonic stacking, but this is just doing a count of all the decrementing paths where you have a top and a bottom. Well, the top is the first number that's bigger than the current y, and the bottom is the current y of the points. Okay, well, so this one is going to iterate over previous points, previous indices. Okay, for each index, iterate over previous indices. keeping track of possible rectangles formed. First rectangle is formed by any y bigger by first bigger y, then points y. And later rectangles can be formed if let's say points y, py is less than or equal to x is less than or equal to that y is less than current y, where current y is the first rectangle's y. Or I guess bigger y, and reset bigger y, and update bigger y. All right, so I don't know, kind of a sloppy summary. Summary. So this ends up being a n-squared approach, as each point from sorted list points is treated as possible bottom right corner of rectangle. Iterate over previous points in sorted list, tracking possible rectangles formed, and then new rectangles can only be formed, or say first rectangle is formed by any bigger y. Later rectangles can only be formed if point y is less than or equal to that y is less than or equal to less than bigger y, and then update that y, update the bigger y to be that y. I'm not sure how I would describe it really. In my mind, it seems like it's like you have a later point, or you have a point that you're working with, and then you find initially anything that's into the top left of it, and then you're just trying to find anything that falls between that height and the height of the y of the point. So then you just find this decreasing path. So it feels like almost like an umbrella. The issue that I had was I had a solution where it was trying to find from this point to anything that is previously smaller than it, like a path of anything of the first thing that was smaller than that. So it just was an umbrella that was the closest umbrella, but then that didn't take into account the height of the current of the starting point y, because that umbrella could actually just dip below, and in theory there could be other umbrellas that were kind of slower or further out, that could also work with this y. So in any case, it ended up being that, yeah, this can be O of n squared. N squared, since for each point need to iterate over every prior point in the sorted list to see what rectangles can be formed. And there wasn't any way that I could figure out to make it faster than that. Note that there is implied, or note that the initial sorting, which is O of n log n, is slower, so therefore this overall speed of this is O of n squared. Like in theory, it'd be O of n squared plus O of n log n, which O of n squared dominates that asymptotically. Space complexity. This can be O of I do a monotonic stack, so yeah, O of n for usage of monotonic stack to help with identification of first earliest prior index with larger y. So this is not necessary. This is just a slight optimization so that when you deal with a later point, you're not, if there's a bunch of points that are smaller than it, that it just skips to something that's bigger than that is guaranteed to be the first point that you would start your rectangle with. If you didn't have that, I think it'd be slower, but still be correct. So yeah, it'd be slower, but I'm not going to bother checking how slow.